Hello students, welcome to 6th video lecture on partial differentiation. In first 5 video lectures, I had discussed these topics. That is definition of partial differentiation, successive differentiation, total differentiation, exact differentiation, differential with examples. Now in this lecture, I will discuss two theorems of differentiation. And these two theorems are very important theorems and they have potential applications in the field of engineering and physics. So let us go to theorems of differentiation. Now let us take x, y, z coordinate system. So this axis I can take x, this axis I can take y, and this axis I can take z. And suppose draw three-dimensional surface, that is spherical surface here, and suppose r is radius of that spherical surface r. So what is the equation of this spherical surface? We write that equation as x square plus y square plus z square is equal to r square. Or so if we go anywhere on this surface, r is constant. R is constant. So and x square plus y square plus z square is equal to r square is satisfied at any point on the surface. At any point on the surface. So we can write this equation as x square plus y square plus z square minus r square is equal to 0. So I have taken one example. So we can write above equation as f of x y z is equal to 0, and this f of x y z, it is equation of this surface and it is also called level surface. Level surface. So f of x y z is equal to 0. This is equation for this level surface, and at any point on this surface f will be 0 or f will be constant. So here I can write, out of three variables, I can take two variables as independent variables and third as dependent variable. So here, if we know y and z, so I have taken here y and z as independent variable. And if we know y and z, we can determine x. And x is equal to what? Plus or minus root of r square minus y square minus z square for this equation. So we can write here x as function of y and z. X as function of y and z. Suppose we take x and y as independent. Then we can obtain z from x and y. So here we can write z, that is function of x and y. Suppose we take y, means here we can take x and z as independent one. So here we can obtain y from x and z. So we can write y is function of x and z. Y is function of x and z. So in this way, for such a function, we can take any two variables as independent variables, and third variable we can obtain from these two independent variables. So in general, if we take some function f of x, y, z is equal to 0. So suppose y and z are independent. Then we can obtain x. So x is function of y and z. So here we have seen total differential. So I can write dx is equal to dabba x by dabba y, keeping z constant, into dy plus delta x by delta z, keeping y constant into dz. Now suppose x and z are independent, then we can write y as function of x and z. So let us call this as equation number 1. So what is dy here now? Dy is delta y by delta x, keeping z constant into dx, plus delta y by delta z, keeping x constant into dz. So let us call this as equation number 2. Now use this equation 2 in equation 1. Means here in the place of dy, use this dy. So we get, so use 2 in 1. So we will get dx is equal. Now delta x by delta y with z constant in bracket. Now dy, that is delta y by delta x with z constant into dx plus delta y by delta z with x constant into dz plus delta x by delta z y constant into dz. So we have used dy here. Now we will arrange this. So solve this one. So first I will get delta x by delta y for constant z into what? Into this delta y by delta x at constant z into dx, plus now this into this. So this into this will get delta x by delta y at constant z into delta y by delta z at constant x into dz plus delta x by delta z at constant y into dz. So I can take dz common. So delta x by delta z at constant y. So now dz is common. dz is common. So dx is equal to this. So let us call this as equation number 3. Equation number 3. Now equation 3 must be valid for any two variables as independent out of x, y, z. Out of x, y, z. So suppose we take case. So suppose x and y are x and z. I will take here x and z. X and z are independent. And we can make dz is equal to 0 and dx is not equal to 0. Then from equation 3, so I have taken dz equal to 0 and dx is not equal to 0. So we will get what? Dx is equal to delta x by delta y at constant z into delta y by delta x at constant z into dx plus 0, because dz is 0. So here now dx is equal to this. So I can write here delta x by delta y at constant z into delta y by delta x at constant z is equal to 1. Now from this I will get here delta x by delta y at constant z is equal to 1 upon delta y by delta x at constant z. Now see here in this one. Let us call this as Roman first. So this relation, it is called reciprocal theorem. Reciprocal theorem. So this relation is reciprocal theorem. And what is that? Delta x by delta y at constant z will be equal to 1 upon delta y by delta x at constant z. So this is first theorem. Now suppose here in the equation 3, suppose we take dx is 0 and dz is non-zero. Dx is 0 and dz is non-zero. So here suppose x and z are independent and we have taken dx is equal to 0 and dz is non-zero. So from equation 3 we get here now, from equation 3 this is 0, this is 0, so I will get 0 is equal to delta x by delta y at constant z into delta y by delta z at constant x plus delta x by delta z at constant y. So we can write delta x by delta y at constant z into delta y by delta z at constant x is equal to minus delta x by delta z at constant y. Now here suppose we use reciprocal theorem. So if we use reciprocal theorem on right hand side, we will get here. So we will get here what? Delta x by delta y at constant z will be equal to, delta y by delta z, delta x by delta y at constant z into delta y by delta z at constant x will be equal to minus 1 upon So for this, I will use reciprocal theorem. So what is that? Dabba z by dabba x at constant y. Now let us take this on this side. So I will write here dabba x by dabba y at constant z into dabba y by dabba z at constant x into dabba z by dabba x at constant y is equal to -1, and let us call this as second. And this equation, it is called reciprocity theorem. And this is second theorem. This is reciprocity theorem, and this is very important theorem. And these equations are also called reciprocity relations, and they have potential applications in physics and engineering. Now we will see simple example. Verify now here first we see to keep in mind. So x here cyclic one, x y y z z x and then x. So it is cyclic one. It is cyclic one. X y y z z x and like that, and is equal to -1. Now verify two theorems for equation of state PV is equal to RT. So we'll verify first theorem first. So I can write here P is equal to RT upon V. So what is dabba P by dabba V keeping T constant? We will get here now differentiation with respect to V. So we'll get minus RT upon V square. We got this. Dabba P by dabba V at constant T is equal to minus RT upon V square. Now this equation I can write V is equal to RT upon P also. So V is function of T and V. Here P is function of T and V. So here we can take dabba V by dabba P at constant T is equal to, now derivative is with respect to P. So we'll get minus RT upon P square. Now let us take these two equations and multiply them. So dabba P by dabba V at constant T into dabba V by dabba P at constant T is equal to minus RT upon V square into minus RT upon P square. So we get here R square T square upon P square V square, and we know PV is equal to RT, so this is equal to 1. So I can write dabba P by dabba V at constant T into dabba V by dabba P at constant T is equal to 1, or dabba P by dabba V at constant T is equal to 1 upon dabba P by delta V by delta P at constant T. So first theorem is verified. Means thermodynamic variable satisfy first theorem. Now we will go to second one. We will go to second one. Now we have to go cyclic one. So first we will take V, P, then T, like this. So here let us take first P is equal to RT upon V. So I will take delta P by delta V at constant T will be equal to minus RT upon V square. We know this. Then V by T. So we can write V is equal to RT upon P. So delta V by delta T at constant P is equal to now R by P. Now next cyclic one, P, V, T, then P. So we have to take delta T by delta P. So if we take delta T by delta P, here we have this one. So I can write T is equal to PV upon R. So delta T by delta P. Delta T by delta P is equal to V by R. V by R. And this is at constant P. Now let us take product. Delta P by delta V at constant T into delta V by delta T at constant P into delta T by delta P at constant P is equal to. Now here minus RT upon V square into R by P into V by R. So here one R will get cancelled, one V will get cancelled. So it is minus RT upon PV, and we know PV is equal to RT. So this one is equal to minus 1. So second theorem is also satisfied by thermodynamic variables. That's why these two theorems are very important in physics and especially in thermodynamics. So this is about two theorems in differentiation. In next lecture, I will discuss chain rule in partial differentiation. Thanks for this lecture. Thanks again.